طيب يعني عزيزم كاتتان باش بابتي أمرومان بريتيلا chapter 4 جرنا نشاني nuclear interactions and nuclear force. Today's subject is chapter 4 titled nuclear interactions and nuclear force in the subject introduction to nuclear force. Interactions of charged particles with matter. There are three charged particles with which we are concerned when we consider general interactions with matter. These are protons, alpha particles, and beta particles. First, protons. Protons are constituents of the cosmic rays that come from outer space, in which case they may have energies above 1 giga electron volt, that's 10 to power 9 electron volt. Protons may also be produced in machines that ionize hydrogen. Energies in this case depend on the characteristic of the machine. There are a few accelerators that may produce protons of energies of the order of magnitude of 10 to 9 electron volt. Most of the humanly accelerated protons only reach energies of the order of 10 to 6 electron volt. Alpha particles. This occurs in nature as the result of the decay of naturally radioactive elements. The energies of the alpha particles from radioactive sources are in the range of 4 to 10 mega electron volt. Alpha particles in this energy range are not very penetrating. They have a range in air of a few centimeters and are stopped by metal foil. Beta particles have a wide range of energies as emitted from radioactive source. The energy of one electron from a given source may be from 0 to the maximum possible value for the source. Beta particles, high energy electrons, may also come from cosmic rays or accelerators, and they have exactly the same property as beta particles. For a given energy range, beta particles or electrons are more penetrating than either protons or alpha particles. A 20 mega electron volt electron will penetrate about 50 centimeters of water. A 20 mega electron volt proton will penetrate about 20 centimeters of water. The ranges of 10 mega electron volt particles in water are electrons 0.2 centimeter, protons 0.1 centimeter, alpha particles 0.01 centimeter. In general, the greater the specific ionization, the lower the penetration. On the average, each pair of ion produced requires an energy loss of 30 to 35 electron volt. Interaction of neutrons with matter. The interaction of neutrons with matter is much more complicated than either that of charged particles or X-rays or gamma rays. For charged particles, we speak in terms of range. For X-rays, we have an exponential law of penetration. Neutrons have no charge, and hence they do not experience repulsive Coulomb forces. They encounter large forces only when they are within a range of nuclear forces. Also, neutron interactions depend on the energy of the neutron. Neutron classification. We can classify the neutron energy in different ranges. They are thermal neutrons, intermediate neutrons, fast neutrons, relativistic neutron energies. Thermal neutrons. The thermal energy range is that in which the energy is characterized by the air temperature. This is an energy range of a few hundredths of an electron volt. For order of magnitude, one can use 0.025 electron volt as the room temperature energy for neutron. Types of neutrons. Fast neutrons are those energies within the 10 kilo electron volt to 10 mega electron volt range. Intermediate energy ranges are those between thermal and 10 kilo electron volt. The relativistic neutrons are those above 10 mega electron volt. The type of nuclear interaction that occurs with the incident neutron also depends upon the type of target nucleus. Neutron capture. There are three types of neutron capture reactions have been found. First, gamma radiation is emitted. For example, one neutron plus aluminum nucleus converts aluminum-1328 plus a gamma. A charged particle is emitted. For example, neutron plus boron will become lithium plus helium. Fusion of the nucleus follows. Neutron plus uranium-235 becomes uranium-236, which also decays to xenon-140 plus cerium-94 plus neutron-21 plus Q, where Q is the energy released in the reaction. Nuclear forces. Nuclear forces, also known as nuclear interaction or strong forces, are the forces that act between two or more nucleons. They bind proton and nucleons into atomic nuclei. The nuclear force is about 10 million times stronger than the chemical binding that holds atoms together in a molecule. This is the reason why nuclear reactors produce about 1 million times more energy per kilogram fuel as compared to chemical fuel like oil or coal. The range of the nuclear force is short, only a few femtometer. 1 femtometer, 1 FM Fermi equal to 10 to minus 15 meter, beyond which it decreases rapidly. That's why, in spite of its enormous strength, we do not feel anything of this force on the atomic scale or in everyday life. The major components of the nuclear force are clearly shown in this graph: short, intermediate, long range. The central force is best analyzed in terms of 3 ranges indicated in the graph. Property of the nuclear force. Some properties of nuclear interaction can be deduced from the properties of nuclei. Nuclei exhibit a phenomenon known as a saturation. The volume of nuclei increases proportionally to the number of nucleons. This property suggests that the nuclear or central force is of short range, a few femtometers, and strongly attractive at that range, which explains nuclear binding. The nuclear force has also very complex spin dependence. Evidence of this property first came from the observation that the deuterium deviates slightly from a spherical shape. This suggests a force that depends on the orientation of the spins of the nucleons with regard to their vector joining the two nucleons. Besides the force between two nucleons, 2NF nuclear force, there are also 3 nucleon force, 3NF, 4 nucleon forces, 4NF, and so on. However, the 2 nuclear force, 2NF, is much stronger than the 3NF, which in turn is much stronger than the 4NF, and so on. In exact calculation of the property of light nuclei based upon the elementary nuclear forces, it has been shown that 3NF are more important. Their contribution is small, but important. The need for 4NF for explaining nuclear properties has not yet been established. Nuclear forces are approximately charge independent, meaning that the force between 2 protons, 2 neutrons, and the proton and neutron are nearly the same when electromagnetic forces are ignored. Thank you very much for your listening and watching. I hope this lecture was also useful for you and wish you all success. Thank you.